Eigenvectors and eigenvalues, right? So where did we get up to? Well, we did the math to work out how to calculate an eigenvalue, right? And that's great, except it's not really satisfying because we don't know what the hell the eigenvector is. The eigenvalue, remember, for the covariance matrix is just the amount of variation along the axis, but we don't actually know the axis itself, right? The eigenvector is that it tells us what the actual vector is. What's the direction of it? So how do we do that? Well, okay, this is what we did. We had this variance-covariance matrix, say, right? 9, 6, negative 2 on the off diagonals, right? And we already worked out how to work out the eigenvalues, and we worked out, hey, look, that's when the determinant is equal to 0. We can solve for that, and that gives us eigenvalues of 10 and 5. Right? So we know that those are the two eigenvalues for my particular 2x2 matrix here. So I need to plug that in to this equation, back into our characteristic equation, to try and get each of the eigenvectors. So each of those eigenvalues has an associated eigenvector with it. Okay? So this is what we know. Well, we know one of the eigenvalues is 10, right? So we know that lambda 1 is 10, and we know that A, this is the matrix A, is 9, negative 2, negative 2, 6 here, times whatever the eigenvector is, or I'll just call this E1, is equal to 10 times that vector, right? So this is self-evident. 8 times the vector is equal to lambda times the vector. Well, we know what A is, and we know what lambda 1 is. Okay, so we need to solve this equation. It's basically a pair of simultaneous equations, right? 2 equations, 2 unknowns, and we can solve this relatively simply, right? In this instance, your equations will collapse down to a single value. E11 plus 2E21 is equal to 0. Okay, so you can choose, in this instance, to let one of the values equal 1, and then you work out what the other value is going to be to get that value of 1. Right? So if we let E21 equal 1, right, we can take this on the other side, then E11 has to equal negative 2. Okay, so the vector is going to be negative 2, 1. Like this. So that's the basic idea, right? You end up just with a pair of simultaneous equations. Now, once again, you're not expected to really do this by hand if it's a complex variance-covariance matrix, but it's not particularly difficult with just a 2x2 matrix or even a 3x3, right? It would be harder to get the roots, the actual lambdas, if it was 3x3. Okay, so you've done that once. We can do it again. So this is a non-unique solution, right? I could have let E21 equal 4 if I wanted to. And if E21 was 4, then E11 would be negative 8. So it would just be a vector. It's still the same direction. The vector would always be the same, right? And that E11 is always in the opposite direction of E21, and it's twice as big. So I can let E21 be anything I like. But it's the vector is given by the actual relationship of E21 relative to E11, right? So I could have, like I said, that could have been 2 and that could have been negative 4. It's the same vector, right? It's the direction. The actual length of that vector is determined by lambda itself, but the direction itself is just the relationship between E21 and E11. So it is a non-unique solution, but all the solutions do lie on that same vector. All right, so let's go through a worked example, because you can't have enough math at 3:30 on a Friday afternoon. We have this matrix, 1, 4, 9, 1. Find the eigenvectors and eigenvalues of A. Right, so this might again be a variance-covariance matrix. Oh, no, it can't be, can it? Why can that not be a variance-covariance matrix? It's not, that's right, it's not symmetrical, is it? We've got a 4 and a 9, right? Nevertheless, so this is not the sort of data this is not the sort of matrix that we would normally invert, but we can do, that we would normally try and find the eigenvalues for. But we can do it anyway. Right, so remember the characteristic equation, a minus lambda I is equal to 0. So we know what a is, right? We're trying to find out what the lambdas are, right? So we want to work out what this is and then work out when the determinant is equal to 0, right? So that's what this is equal to. A minus lambda I is equal to 0. So that's here we go. 1 minus lambda, 4, 9, 1 minus lambda, right? So remember the determinant is going to be those two things multiplied together minus those two things, right? So that's 1 minus lambda squared minus 36. 4 times 9 is 36, right? So we need to solve for that. And the answer is going to be, I don't expect you to calculate it right straight off the top of your head. If lambda is negative 5 or 7, then we have a value equal to 0, right? If lambda was negative 5, right, 1 minus negative 5 equals 6. 6 squared is 36. Minus that is 0, right? Likewise, if it was 7, then we end up with a negative 6. Negative 6 squared is 36, equal to 0. Right? So you could solve that using the quadratic, the little formula that you learn. Or you can just work it out if you're clever. But the main thing is we've got our lambdas now, right? We've got our eigenvalues. Now we can just plug those into the equation, right? Negative 5 and 7, we'll do them separately to work out our eigenvectors, right? So we know what A is. Let's start with, well, normally we would actually say this is the bigger lambda, so we'd start with that one, but we're just going to start with lambda 1 is equal to negative 5. It turns out, well, I haven't actually done the math here, but it turns out that, in fact, the vector 2, negative 3, or vectors in that direction are going to be is going to be the solution. And likewise here, if that was a 7, then it would be 2, positive 3. Okay, that's just your substitution. All right, so where are we? So we have basically used mathematics to analyze a square matrix, right? So the eigenvalues, the eigenvalue decomposition finds some sort of, what have we done? We've found an orthogonal basis in our k-dimensional space or our p-dimensional space. I normally talk about p-dimensional space. I don't know why I threw a k in there. So the eigenvalues you'll find in your eigenvectors are important in a lot of ways. We'll use a variety of techniques. The good news is, in general, right, you don't have to do this by hand. The computer is going to do it for you, right? But it's still very useful to understand, I think, the basic maths behind it, so you get some idea of the intuition of what it's doing, right? Remember with a variance-covariance matrix, if we have some data, what is it doing? The variance-covariance matrix is acting to create, the transformation is basically along those axes, and the axes that it draws are actually PC1 and PC2, right? And that's why the eigenvectors are going to go down that line. So we basically, SAS follows what everybody does, which is to list the eigenvalues from the largest to smallest, right? And this is useful because obviously that first PC is the one that explains the most variation, right? It's also useful if you're doing collinearity diagnostics, explain variation in the model, right? In the data or the model. So we know all about this. I don't really have to describe it anymore. And this was simply an example. Let's just recap. This was an example of the data were completely uncorrelated, right? Well, they were generated using an uncorrelated mechanism. So the correlations that we saw were just very small and due to sampling error, right? And so what happened when we did an eigenvalue deconstruction of the correlation matrix there? Well, all of the eigenvalues were roughly the same size. Obviously, it always ranks them from biggest to smallest, but that's just due to the chance of these very small correlations that happen. So there's no real meaningful difference between these guys, right? It's like trying to draw an axis that explains the most variation through this data cloud, right? Okay, it happens to be this one, but it could easily be that one or that one. They're all roughly the same. They all explain roughly 33% of the variation, right? So in this instance, PCA didn't help very much at all. But if there was structure in the data, real stuff, this is obviously an artificial example when in fact there is a great deal of structure in the data. The data don't lie in the three-dimensional space, that lies on a two-dimensional subspace. What happens? Well, we know that, of course, since we're dealing with the correlation matrix, right, the eigenvalues all sum to 3 because there's 3 variables, same thing here. And in fact, the sum of the first 2 eigenvalues is going to be 3, right? So the first eigenvalue pretty much explains 2/3 of it, and the last one explains 1/3 of it. And that last eigenvector, right, since all the data basically lie on a plane, that last eigenvector is going to be 0. It doesn't really exist. But SAS can still calculate it, even though you would have problems trying to do it by hand, potentially. Right, so we can do this for any square matrix, eigenvalue decomposition. Right? Hopefully we can decompose it. If we have a rectangular matrix of some kind, we can still decompose it. We have to use something called singular value decomposition, SVD. In your data mining course, we use an SVD to decompose some data. It's very useful if you have a lot more variables in rows, because your standard methods of decomposition don't work very well in that instance. So singular value decomposition is what's typically used for a rectangular matrix. It's more general than eigenvalue decomposition. Actually, what it does is it factorizes your matrix into what's called singular values, but these are analogous to interpreting your combinations of the rows and of the columns, and it can be used to calculate an inverse as well. But to be honest, this doesn't really matter. This is just really for your notes and your general information, because you don't need to do that with your PCA. Right, so how do we summarize? Well, SAS is going to do all your necessary calculations, right? Your expertise is not going to be in the math particularly. It's going to be in the interpretation of the results. So you need to be au fait with what the PCA is, right? How you got to it, which I think you understand now, hopefully. How you got to the PCA. Well, what's that PCA1? It's that it draws an axis, conceptually, it draws an axis that has maximized the variation through my data cloud. And the second one was orthogonal and does exactly the same thing, right? And then I've projected the data points onto those pair of axes, right? So you've got a conceptual understanding, and that's the important thing, the interpretation of the results, right? But the matrix algebra sort of helps with that. So what do? Well, we can do, our raw data matrix to the variance-covariance matrix, the eigen deconstruction of that. This is sort of talking about, I guess this is an example of what's going on. We now know, well, these are the eigenvalues, right? These are the PCAs, the eigenvectors of this particular covariance matrix. So if I've got a covariance matrix 5, 0, 1, right? So 5 and 1 on the diagonals and 0 on the off diagonals. What's that? That means that there is no correlation between variable 1 and variable 2, right? And so my data cloud is going to look like this. There's no tilting to it. So as a consequence, what's my first eigenvalue going to be? My first eigenvector is going to be. It's just going to be determined by, I'm trying to draw an axis that contains the most variation. It's just going to be given by variable 1. It's in fact your PCA, your eigenvector, is just going to be heavily weighted to V1, variable 1. And your second eigenvector is just going to be variable 2. Right? And that's all that's going to happen. And the variation of that is going to be that the length of this vector is going to be equal to the actual, the variance itself. And I could converse this, I could flip that around, and I'd get the same sort of thing with V2 and V1 here. So, okay, so take-home messages. If the covariance matrix is diagonal, the covariances are 0, the eigenvectors are going to lie parallel to the axes, right? So a diagonal matrix, remember, is a matrix where you've got values on the diagonal, but everything is 0, else is 0. That's sort of the unusual case. That's the case where you don't have any correlations between any of the variables, so you can't really reduce that dimensionality very easily, right? All you can do is say, hey, look, well, the first variable is the most variable one, this variable here, so is that useful to me? It's a bit of a pathological case. You can't reduce the dimensionality of that very easily. Right? If the covariances, however, are not zero, then you've got structure in the data, and you can think about being able to reduce that through PCA. Right? And your eigenvectors, remember, are just those axes that go through that data cloud that represent the variation along the longest axes. We've already done this. I don't think we need to do that again. This is more for your notes' sake. This is just a second example in case you want to work through it. Okay, but there's a bit more to it, right? So here we get, remember how we get our eigenvalues and there is a non-unique solution to it, so I could have made it as long as I wanted to. The eigenvectors, they could have been 4, 2, or 3, 1, or 1, 1, or 1, negative 1. So if I was to quickly work through this, I will quickly work through this maybe. Right, so we have a matrix 3, 3, negative 2, negative 2, right? So covariance matrix very clearly. I do the eigenvalue deconstruction. I end up with, this is one we've done already, right? And eigenvalues of 5 and 1. Right, and then I try and find the corresponding eigenvectors. So the eigenvector for the 5 comes to this 1, 1 solution here, or 1, negative 1 solution here, right? And the 1 eigenvalue is associated with a 1, 1 eigenvector. Now, typically, what people do is they normalize the eigenvectors. What does that mean? Any idea? It's just a rescaling. You're rescaling that vector so that it is of length 1. That's all. Right? So it's just of the standard length 1. So if you think about a vector that goes 1 unit this way and 1 unit that way, how long is it? Square root of 2, right? It's a little bit longer. It's like 1.41. So we're just going to shrink that down so it's only of length 1. Right, which is 0.71, 0.71, something like that. Right, so to normalize it, all we're doing, and this is going to look complicated, but it's not really conceptually, is you divide each element by the square root of the sum of the squared values. Right, so all I do is I take every element here and I square it. Right, it's just Pythagoras' theorem is all it is. Right, I square all these values, and then I sum them all together, and I find the square root of it, right? And that's just the length of the vector in its current form. So if I divide by that length, then I get the normalized value, right? So what I want to do typically is calculate or what people often do is calculate the normalized eigenvector, right? So remember. Oh, so draw, in fact, the next spot might actually show it. Okay. This was my eigenvector, right? It was 1, negative 1. So 1, and then, oops, negative 1 here. So what's that distance? That distance is, well, 1 unit, 1 unit. Remember Pythagoras' theorem? A squared plus b squared equals c squared. So that turns out to be a distance square root of 2. So by dividing it by square root of 2, that means that distance now, if it's now 1 root 2, well here, 1 root 2, 1 divided by root 2, this distance here is only of unit length, just a distance of 1. Right? So that's all we're doing. We're just shortening this vector so that it's only of length 1. Right? So what does it mean? So normalization is simple. It's just finding the length of the vector and rescaling it so that the length is equal to 1, right? And that's what we do here. So for any normalized vector, right, the inner product is going to equal 1 of that. So if I take this vector, right, and I transpose it and then multiply it by itself, right, it's like I'm finding the square of it, well, we know it's at length 1, so it's just going to equal 1. Right? In other words, 1 divided by root 2 minus 1 divided by root 2. If I multiply those two things together, I just have a value of 1. Right, so here we have, this is what we've got. We have for the eigenvalue lambda 1 equals 5, this is my associated eigenvector after it's been normalized. Right, and this is the form that a lot of people like to use. In contrast, the normalized eigenvector for lambda 2 equals 1 was very similar, except it is of course in 90 degrees to it, right? So if this one is facing in this direction, we know the other one is going to be in this direction, right? Because it has to be orthogonal to it, right? It has to be at right angles to it. So that's 1 over root 2, 1 over root 2. So that would be in this direction, which is at 90 degrees, right? It's a new basis. Okay, so what they call this, using the normalized eigenvectors and the eigenvalues, is called a spectral decomposition, or sometimes a spectral factorization of my matrix A. What it's doing is breaking up A into pieces determined by the spectrum of A. In other words, determined by the eigenvalues. Right? So each term in this equation is an n by n matrix, and E prime, right, are going to be, is basically the projection matrix of X. Right? What does that mean? It means if we multiply this E prime, or E transpose I should say, this is the eigenvector times the transpose of the eigenvector, it projects that point onto the actual axis of the eigenvector. Right? So this is the math that's used to actually find the new coordinate space, basically. Right? You've got your original data. Right? Think about it this way. You've got your original data. Here's your eigenvector here, E1, right? But basically, we want to find that coordinate space. What's the value here? Here's 0. We want to know how big that is, right? This is the projection from the original data onto this to give us these values, right? So basically, we've got this, and so this data point might have been rotated, and we have a new coordinate system, PC1, PC2, and that's going to look flat like this. So we're going from here to here using that E prime, or E transpose. It's the projection matrix of X. Right, so that times X gives us a new coordinate system.
Do we need to know the reason why?
You need to know the math, why that would occur?
Yeah.
No, not really, no. All you need to know is, well, this is the shorthand matrix way of doing it if you wanted to.
Okay.
More important to me is that you understand conceptually what you've done, which is, well, okay, I've created these new set of axes through the data, right? And so for any data point, I have a new data point, right, that has a new set of coordinates. It's going to be in the same relative position relative to the other data points, though. So what is that coordinate system? Well, I can work it out using E prime if I want to. Okay, so where are we? We're up to the spectral decomposition, right? Okay, so for your eigenvectors, the scalar product is equal to 0, E transpose E. For this P matrix that we're going to calculate, the P matrix is basically the matrix that comprises of all of your eigenvectors. So if we get all our eigenvectors, right, and we line them up in columns, we have this new matrix P, right? So P is going to be square, symmetric, and orthogonal, right? So remember, this is just your first eigenvector here. This is just your second eigenvector. And this is going to create this new matrix, which we'll call P. So we're going to use P for the, do we care about this? Particularly the scalar product is equal to 0. for your eigenvectors, we know that the scalar product between the eigenvectors, between E transpose 1 and E2 is going to be 0. And that's because they're all orthogonal to one another, right? So the scalar product is equal to 0. The scalar product with itself, as we know, is equal to 1. We just worked that out before, because that was the length, right? The scalar product of a row or column with any other is equal to 0. I've done that already. Why? I'm not sure why I put in that twice. Or with any other. Okay. So, right. E prime 1 times 2. E2 is equal to 0 because they're orthogonal. Right. We know that E prime 1 times E prime 1 is equal to 1 because they've all been normalized. And the fact that any combination of these things on the off diagonals is going to equal 0 because they're all orthogonal to each other. So that I could put down E prime 1, E prime 2, E3, I should say, and that would also be 0. So what do I mean by orthogonal, right? Geometrically, we know what it means. We know that it means it's sitting basically at right angles to one another. These vectors are perpendicular to one another. But conceptually or statistically, that means they are linearly independent. Information about one axis tells us nothing about information on another axis. Right? We have no more correlations left over. So this is how it decomposes, basically. We've got our matrix A. Remember, we're trying to decompose it. Basically, we're splitting it into our eigenvalues and then our eigenvectors. Right?
Sorry.
Okay, so this we can just